We have sensory receptors in our body that respond to stimuli. When our sensory receptors and nervous system receive and represent stimulus energies from our environment, we call this sensation. Perception is when our brain organizes and interprets sensory input. Under normal circumstances, sensation and perception blend into one continuous process. Every night when I go to sleep, I turn on a white noise machine to help block out the noises in my house. So after a while, I stop noticing the hum. Yet every time the power goes out, I immediately know because I'm suddenly aware that this noise has stopped. This is called sensory adaptation. I developed diminished sensitivity to my white noise machine as a consequence of the constant stimulation of it. My nerve cells started to fire less frequently in response to the stimuli. Sensory adaptation offers important benefits. Remember when we talked about selective attention? So same concept here. Sensory adaptation allows us to have the freedom to focus on important changes that occur in our environment. Our sensory system is alert to novelty, and it gets bored with repetition. Perceptual sets are a set of mental tendencies and assumptions that affects top-down, what we hear, taste, feel, and see. So with top-down processing, we construct perceptions of sensory input by drawing on our experiences and expectations. So when you look at this picture, if you look from the top and you move your eyes down, you might expect to see 12, 13, 14. However, if you move your eyes from left to right, you might expect to see A, B, C. Because the image in the center is a bit ambiguous, our brain deciphers what the characters should be based on the context of its surroundings. So what determines our perceptual set? Through experience, we form concepts or schemas that organize and interpret unfamiliar information. Our pre-existing schemas for things like mountains and deserts influence how we apply top-down processing to interpret ambiguous sensations. Our perceptual sets are also influenced by motivation and emotion. Motivations can bias our interpretations of neutral stimuli. For example, if we're thirsty, then a water bottle may appear closer to us than it really is. Emotions can move our perceptions in one direction or another. For example, upbeat music can speed up our identification of happy emotion words and make it easier for us to spot happy things in our environment. Much of what we perceive comes not just from what's out there, but also from what's behind our eyes and between our ears. Through top-down processing, our experiences, assumptions, and expectations, and even our context, motivation, and emotions can shape our views of reality. There are two main theories of color vision that we'll cover. So the first is the Young-Helmholtz theory. This theory states that there are three main types of color receptors, one of which is most sensitive to red, another to green, and another to blue. When they're stimulated, they can combine to produce any color. For example, when red and green wavelengths stimulate red-sensitive and green-sensitive cones, we see yellow. Men are more likely than women to experience color deficit vision. About 1 in 12 males are colorblind. Typically, they lack fully functioning red or green-sensitive cones. The picture of these stoplights shows you what someone with color blindness might see when they come across a stoplight. The Young-Helmholtz theory helps explain color blindness. The Young-Helmholtz theory doesn't fully explain color vision, though. While I'm talking, I want you to stare at the image on this slide. The opponent process theory says that color vision depends on three sets of opposing retinal processes: red-green, blue-yellow, and black-white. Neurons in both the retina and the thalamus are turned on by red, but turned off by green. Others are turned on by green, but off by red. Therefore, red and green are opponents. We either see red or green, not a reddish-green mixture. However, colors that aren't opponents can mix together. For instance, red and blue can combine to produce a magenta color. Now, if you stare at an image such as the one above, then we might tire some of these receptors. By now, your receptors for green might be starting to wear out. So what happens when I take away the image and show you a white background? White contains all the colors, including red. Because you tired your green receptors, only the red part of the green-red pairing fired like normal. Both the Young-Helmholtz and the opponent process theory have something to contribute to the theory of color processing. So color processing occurs in two stages. The retina's red, green, and blue sensitive cones respond in varying degrees to different color stimuli, as the Young-Helmholtz trichromatic theory suggests. The cone's responses are then processed by opponent process cells, as the opponent process theory states. We understand and organize our perceptions using a gestalt, meaning a whole. Our conscious perception is organized into an integrated whole. One way that we organize information about our world is through form perception. We need to be able to organize information into both a figure and a ground. This means that we do things like separate faces from their backgrounds. We perceive when objects, so the figure, are distant from their surroundings, or the ground. In the figure ground example above, we may first see the faces. In that case, the white part of the image would be the ground, and the faces would be the figure. We can also switch our perceptions. The white part can be seen as a vase, and the black part of the image becomes the ground. We also use grouping. Our mind brings order and form to other stimuli by following certain rules for grouping. We may group things based on proximity, similarity, continuity, closure, or connectedness. These principles help us to construct reality, although they do have the potential to lead us astray. We're able to see our visual world in 3 dimensions, and we can judge distance. So we perceive depth in part due to binocular cues. Binocular cues depend on the use of both of your eyes. Convergence is a binocular cue where the inward angle of the eyes focus on a nearby object. Retinal disparity is another cue. Because there is space between your eyes, each retina receives a slightly different image of the world. By comparing these 2 images, your brain can judge how close an object is to you. The greater the disparity or difference between the 2 retinal images, the closer the object. When there isn't much difference between the images cast on our right and left retinas, we use monocular cues. This includes things like relative height, relative size, relative motion, linear perspective, and interposition. Perceptual constancy is a top-down process where we perceive objects as unchanging even as illumination and retinal images change. So color constancy refers to our ability to perceive colors as relatively constant over varying illuminations, so different light sources. We see color thanks to our brain's computations of the light reflected by an object relative to the objects surrounding it. So the cube above demonstrates the ability of a blue object to appear very different in 3 different contexts. Yet we have no trouble seeing these disks as blue. Nor does knowing the truth that these disks are identically colored diminish our perception that they are quite different. Because we construct our perceptions, we can simultaneously accept alternative objective and subjective realities. Brightness constancy, also called lightness constancy, similarly depends on context. We perceive an object as having a constant brightness, even as its illumination varies. We also have shape and size constancy. With size constancy, we perceive an object as having an unchanged size, even while our distance from it varies. We assume that buildings far off in the distance are tall and can hold lots of offices within them, even when they look small from far away. With shape constancy, we perceive that shapes are the same, even as they change position. For instance, even though the doors above look more like a trapezoid as they open, we perceive them as still being a rectangle.